about some experiments that were done at SRI last year. Um, the DARPA program under which the contract work was done ended at the end of August, and so I'm going to be talking about experiments from the end of August and September, October, November, December, up through earlier this week. Okay, so as Mitchell argued, I've been interested in particular about how energy exchange works. For example, in experiments showing excess heat, nuclear things are going on, but we don't see the energy as energetic nuclear radiation. And what that means, from my perspective, is that the nuclear energy itself is going into other degrees of freedom, other channels. We don't have diagnostics for that in the Fleisch and Pons experiment, and that's been worrisome. So I'm going to, in a talk tomorrow, I'll be exploring those issues much further. But the motivation for my interest in this experiment, as Mitchell has correctly described, is that I'm thinking that what's going on in Carabut's experiment is that energy is going from the vibrations into causing excitation of a nucleus. I think that's the significance of it. Not everyone agrees. Vladimir. No, Vladimir has other ideas about how this happens, as he'll explain in the following talk. But having made such a statement, it's testable. So let me start. The idea is that Carabut's experiment shows collimated X-ray emission at 1.5 kilovolts. I should point out that an early experiment by Gotzi showed collimated gamma emission near 90 kilovolts. Kornilova and Vysotsky also see collimated X-ray emission, and I'm convinced that it's closely related to Carabut's experiment. I'm convinced it's also closely related to the experimental results I'm going to show shortly. Collimated X-ray emission, in my view, is an unexpected effect. In my view, it's not consistent with the physics you can find in your textbooks. As Mitchell mentioned, there's a theoretical picture, but independent of the theoretical picture, and I don't think there's going to be much in the way of theoretical picture in this presentation, the conjecture is sufficient to be tested experimentally. So that's the goal. So let me talk briefly first about Carabut's experiment. I visited Carabut's lab before Carabut saw this effect, and we had a version of his glow discharge in our lab, and I got to take data on it and work with Louis Smolin on it for about 4 years. And so I have an appreciation both of the discharge of the electronics that Carabut used and so forth. So he popped up at ICCF 9 saying that he'd made an X-ray laser. And having myself worked on X-ray lasers some time ago, I scratched my head and I said, you know, are you sure? And basically the cathode's down here, the anode's here. Usually he's got 5 or 10, maybe 20 torr of gas. So he's got a discharge between cathode and anode. In this particular version of the experiment, X-rays are coming up off the cathode and going through an extension that he added in order to measure it. He added this extension because he wasn't sure whether he was seeing electrons or X-rays. So he put magnetic field here to try to deflect the charged particles. So what ended up going through at the end, he had a demonstration, was not charged particles. The conclusion is that they're X-rays. So he's done many measurements. He gets X-rays coming out collimated. So over the years, I was curious about what the spectrum looked like. So for example, in his early experiments, he used filters and scintillators and luminescent detectors, and he got various averages of the X-ray energy. But I was curious as to what the spectrum looked like. And at some point, he put together a bent mica spectrometer. So the X-ray comes up, it's a bent piece of mica, and goes onto film. And he sees signals like this. So if you like, here's the calibration. And my friend Alexander's, he's very good at glow discharges. He's not an X-ray spectrometer person, so he's calibrated with a flat mica formula. So there are some corrections. But here's 1 kilovolt, here's 2 kilovolts, and here's broad radiation in the neighborhood of 1.5 kilovolts. So this is broad, this is diffuse radiation as opposed to sharp radiation, which he also sees. But today I'm most interested in this diffuse radiation. So here is palladium as the cathode, helium as the gas. The earlier one was aluminum as a cathode and helium as the gas. This is not cold fusion per se. There's no palladium and deuterium. In the other one there was palladium, but we're seeing here aluminum is giving the collimated X-rays as well. As does tungsten and titanium, copper, molybdenum, all kinds of other things he's tested. There are many different metal cathodes which he can work with, which give the collimated X-rays. Additionally, so helium gas doesn't have very good solubility in aluminum or palladium or any other metal as well. He also sees the effect with krypton, with neon, with H2, with D2. So the gas doesn't seem to matter. It doesn't have a big impact on the spectrum or the presence of collimated X-rays. So here's a trace he made from one of his spectra. It peaks around 1.5 kilovolts. It's broad. In terms of the broadness, when he runs at low voltage, you can get it to be narrower. When he runs at high voltage, it can be a little bit broader. So features, similar emission, variety of different metals, similar emission for different gases, spectrally broad, namely, if you do X-ray spectroscopy, when you see an X-ray line, it tends to be sharp, so you look at it and you know it. And when he runs with krypton, for example, he can get a characteristic X-ray in the spectrum which looks sharp. So it's not that a spectrometer is a terrible spectrometer with bad resolution. The feature really is broad. Now the peak can occur at different energies. So you have this feature, so here's 2600 volts, here's 4150 volts. So this is a stronger glow discharge, this is a weaker glow discharge. You see here this might be a little bit lower mean energy than this one. So there is some variation of the centroid of this thing, which in my view depends in his experiment more on voltage and less on the metal. Although in glow discharge, the metal and voltage they're interacting. To get the same current density, you may have to run a higher voltage in different metal. Okay, and from other observations, they originate either from the cathode surface or one cannot, from the observations, rule out originating from the gas just above the cathode surface. I don't actually think it comes from the gas. I think it comes from the cathode surface. Input from theory generally. Collimated X-rays are interesting. They're not so easy to produce. You need to do some work to collimate. So for example, if you have a lot of X-rays isotropic, you can pass them through a pinhole, go away, so if you have another pinhole, and what comes out will be collimated because of geometry. But these are collimated born right near the cathode, and when they go up, so they're born collimated. To be born collimated, either you have to have an X-ray laser, or else you need phase coherence among the emitters. And this is a tough thing. Having spent a lot of years trying to make X-ray lasers, I know how difficult it is to make an X-ray laser. And I'm sorry, but you can't run a glow discharge and then expect it magically to make an X-ray laser. If you're going to make an X-ray laser, you need high power, you need a scheme, you need to do work to arrange your excitation to be where you want, when you want it, and so forth. Arranging for phase coherence is marginally easier, but in a glow discharge, what's the source of phase coherence? I mean, that's very much not obvious. Another issue has to do with the temporal features of the emission. And although I didn't show it, the sharp features originate after the discharge is turned off. So he turns off the discharge, has Russian electronics, so he gets a current spike, voltage spike. Well, the discharge the plasma can help get him a spike as well. And then after the current voltage has turned off, a millisecond later, this thing can burp out some collimated X-rays. And this by itself adds more difficulty. So for example, if you imagine you have a way to make an X-ray laser, you promote an electron to a state up 1.5 kV, well, it's not going to stay there for very long. I mean, lifetimes, a picosecond would be an eon for an excited electron up 1.5 kV, but we're talking about a millisecond. So arranging for a population version that lasts a millisecond is basically unthinkable. So electronic states decay. Nuclear states tend also not to have particularly long lives, unless there are a few known metastable states which do have long half-lives. In a sense, if you ask when the discharge turns off and you have this voltage and current spike, what degree of freedom can have energy hanging around for a millisecond? Well, the voltage spike, there's issues, but there's a conduction path up near the surface of the cathode, and there's the cathode, so you get a giant voltage spike, so you can imagine that maybe you get the cathode ringing. So the cathode rings, and if you calculate what the fundamental frequency is, and you say, what's the lifetime of the acoustic vibration, a lifetime on the general order of a millisecond is sort of possible, but that's kind of the only degree of freedom in that's going to retain any energy for a millisecond, at least from my perspective. So all of this gives us a gigantic theory headache. So electronic transitions, if it was going to be electronic transition, it ought to have something to do with the gas or the metal. But since the collimated X-rays don't care much about the gas and don't care much about the metal, we get a theory headache. Low energy nuclear transitions are rare from the ground state. If you're up at very high energy, the density of states is high, so you can have smaller differences between states. But a nuclear transition near 1.5 kilovolts is not the kind of thing that you're going to find in molybdenum and tungsten and so forth and so forth. Lifetime is a theoretical headache. How do you get excitation? For example, in some cases, the applied voltage under conditions where the X-ray signal is observed is less than the X-ray energy. And if it's going to be coherence for phase coherent emission, how in the world do you get phase coherence among the different emitters? Anyway, all of this ends up leading one to the conclusion that somehow this needs to be connected to the vibrations in some way. Let me turn to the nuclear problem. In terms of the models and theories I worked on, I was motivated to look for transitions from the ground state, because there's various enhancement factors if you've got a lot of the ground state around. So if you look in the Brookhaven nuclear database, the BNL NUDAT database, and you search for all stable transitions from the ground states up to certain levels, well, here's the cast of characters. Mercury 201's around 1.5 keV, tantalum 6.2, that's the next one. Down here is the iron 5714.4. So you might look at that and say, aha, 14.4 kilovolts. That's got to be the Mossbauer transition in iron that's so famous. And it is. So here it's number 1, 2, 3, 4, 5, 6, 7. So 7 on your list of transitions. So as you can see, these are pretty rare beasts. So here it is. And probably, I mean, based on what on Mitchell's introduction, what I've said so far, the basic thought is that if there is a path to convert vibrational energy to nuclear excitation, you want the nucleus that's got the lowest excitation energy from the ground state. So mercury 201, that's it. So the thinking is there a way to start from here and absorb a lot of quanta, vibrational quanta, and make your way up to here or close to here? So that's what's under discussion. Now, if you succeed, if you get up to here, the lifetime has been measured experimentally to be about 81 nanoseconds, and it's dominated by internal conversion. So the way internal conversion works, and make a note of this because you're going to be tested on it at the end, is that the nucleus is excited and you have an electron, the nucleus goes down, the electron gets kicked out. So it'll be an electron with some probability of being near the nucleus, so it'll be an S-shell electron. The outermost has lowest probability of least energy, so it's going to come out the most. The next one in will have be deeper, be closer, but it's not going to have as much energy when it comes out. The K-shell is going to be too deep to come out, and so forth, and so forth. So all the internal conversion probabilities have been calculated, and they're tabulated, and they're available. So that part of the problem is understood. Now, for radiative transition, the radiative half-life is it's not known precisely, but it's about 4 milliseconds. So if you produce an excitation, most of the time you're going to get an electron coming out rather than an X-ray. X-ray is only going to happen a small fraction of the time. So if you're going to test the notion that you go from here to here by a gazillion vibrational quanta, and for the vibrational quanta that we're going to be talking about, it's on the general order of 10 billion of them. So, you know, probably you'll immediately scratch your head and say, well, clearly he's lost his mind. There's no way to stack up 10 billion. But let's keep going and see what happens. So the supposition is that maybe vibrational energy can be converted to produce nuclear excitation. Lots of theory suggesting that this might be true, and some of this theory will get talked about tomorrow. So let's now put it to the test. So to be tested is going to be this piece of copper foil. Piece of copper foil, roughly 73 microns thick. It's yay large, not particularly large. Nothing special about the copper foil. We tended to use the word plate for historical reasons. So we're going to put another piece of copper next to it, a big piece of copper, and we're going to form a capacitor here, and we're going to drive it with AC. So when you do that, you get a field that points this way, then a field that points that way. It goes back and forth rapidly. Now, when there's a field there, the two plates are attracted to one another. They pull each other together, and they pull each other together independent of which direction the field's going to point. It's a capacitor energy.